The last lesson in multivariable calculus in our textbook, 16.9, the divergence theorem. This theorem relates a surface integral, that is the flux, with a triple integral involving the divergence of a function. So really what we're going to see is that this surface integral, this flux, could be rather complicated, especially if you have a difficult surface to work with, especially one with multiple faces of the surface, and perhaps a sphere might be a little bit of work. It could be a longer problem, but look, there's an alternative that we can do instead of working out this flux surface integral. We could turn this into a triple integral, something that we did last chapter, with the divergence of f as the integrand is what is inside. Now, recall that if f was defining your vector field with p, q, and r, the divergence for f, remember that was like the del operator with the dot product here. That really just became the partial derivative of p with respect to x plus the partial derivative of q with respect to y plus the partial derivative of r with respect to z. If you could figure that out and then evaluate that triple integral, this problem becomes a lot simpler in many cases, finding that flux integral in this easier review problem. So let's take a look. We've got f. Of course, f is going to be defined as z, comma y, comma x. And let's go ahead and first find the divergence of f here. So what we'll have is the partial derivative of z with respect to x plus the partial derivative of this y here with respect to y, and we'll have plus the partial derivative of x here with respect to z. Well, the partial derivative of z with respect to x is 0. Partial derivative of y with respect to y is a 1. Partial derivative of x with respect to z is a 0. Our divergence is just a 1. So as we're asked to find this flux here, this now becomes a triple integral of 1 dv, and our surface in this case is a unit sphere. That's the solid. We could work this out. Now, of course, we could go to spherical coordinates and think about how to work this out. However, there's a shortcut in this problem. As we look particularly right here, we can see that when you had a 1 inside of this triple integral, this would refer to the volume of that solid E. And the volume of a unit sphere is 4/3 pi r cubed. We have a geometric shortcut here. That's with an r of 1 in this unit sphere. So this problem just becomes 4/3 pi. So that's a quick introduction. Let's very quickly take a look at our last problem of the day. Here's example 2. We're asked to evaluate the flux where f, of course, is going to be this xy, and then we've got y squared plus e to the x z squared, and then we'll have for our k component a sine of x comma y, or a sine of xy, I should say. And as we look at this, this is technically an old problem from 16.7. Find that surface integral. Find that flux, and remember, flux has to be applied to a surface. Flux was really the rate of flow over a surface. And the surface this time is a little bit more complicated. S is the surface of region E, and it's bounded by a parabolic cylinder, z equals 1 minus x squared. And if we looked at z equals 1 minus x squared, imagine that we just went ahead and we graphed on the xz plane 1 minus x squared. Well, you would get something that looked just like so. This would be z is equal to 1 minus x squared. We'd be going between x is 1 and x is negative 1 and positive 1. But this cylinder would be applied for every possible y value. We could have a y value of 0, a y value of 1, a y value of 2, and so forth. So you can see really what is getting traced out here. You can see this parabolic kind of a cylinder. There's that parabola, but that parabola is going to get repeated for every possible z value. We're going back to the very start of the course. You know, you have that parabola here, you get a parabola right there, and that's your cylinder, that cylindrical shape. But of course there's more to this, you know, surface, or this region E, this solid region E that we're talking about. It's bounded by that parabolic cylinder. Z equals 0 is the xy plane that we're so used to graphing on. Y equals 0, well, I just traced that out in red right here. You know, this is y equals 0. And then y plus z equals 2 is another plane. That's right here that they're tracing that thing out there for you. So you can pretty much see we've got that parabolic cylinder, we've got the floor z equals 0, we've got y equals 0, and then we've got this y equals 2 minus z. And wow, what a solid. First of all, going back to what we had seen earlier in the week, you know, we started the class off on the other day talking about flux integrals. And, you know, the flux integral that we were wrapping up with, going back to 16.7, you know, we worked it out okay. We were able to work it out. But look, example 2 had a surface S1 and then a surface S2, and, you know, all together that solid, that surface that, you know, would be encompassing that solid, you know, it really just had 2 parts. We had that paraboloid, and then we had z equals 0, that green highlighted part, and that actually was something that we had to consider. We had to look at that bottom portion. So, you know, when we found the rate of flow, the flux over that surface, we had to consider all faces of that surface. You know, when we're looking at the last lesson of the year here, 16.9, all of a sudden we're going to see that, wait a minute, this solid really has a lot of complexity to it. How many faces does this solid have? Well, you know, we've got this right here, the y equals 2 minus z. We've got the floor. We've got, you know, right over here, this part of the solid. We've got the part where you know, that parabolic cylinder is meeting with y equals 0, the y equals 0 part. And before too long, you could see that we've got multiple faces, 4 different faces that we'd have to consider. And that, as a surface integral, is not what you want to have to deal with. So the divergence theorem really does come to our rescue tremendously. So we're going to say, look, rather than work out the flux, let's instead try to work this out. The divergence of f evaluated over this triple integral, the triple integral over the solid E. Maybe, just maybe, that's easier. And indeed it is. But let's go ahead and first find the divergence of f, that's going to actually go pretty quickly. I'm going to slide this down a little bit. But what we'll say is the divergence for f, well, we're going to have our partial derivative of xy with respect to x plus our partial derivative of y squared plus e to the xz squared with respect to y plus the partial derivative of the sine of xy with respect to z. And here, taking our derivative of xy with respect to x, you just get a y. The derivative of y squared plus e to the xz squared with respect to y would be a 2y. And our last component, there's no z in there. Everything's considered a constant. You just get a 3y. So delightfully, we're now saying, hey, can we break this integral down like we did in chapter 15? Here's our integrand of 3y. Let's look at our solid. And remember, there were three types of solids. There was a type 1 where z had boundaries. There was a type 2 where x had definite boundaries. This is a type 3 where your y could be thought of to have very definite boundaries. So if we were to immediately start integrating with respect to y, I hope you'd know that y would be spanning from y equals 0. The largest it could get up to would be this plane 2 minus z. Then we could condense that solid onto the xz plane. And guys, the wonderful thing is, as you do that, as you condense the solid to the xz plane, you're going to really just wind up with what we started off with right here. You could say, hey, as that whole solid is condensed, imagine that we're just saying, look, we've dealt with our y. Now let's deal with our remaining boundaries. Here as you look, I hope you can see pretty clearly that z has some definite boundaries. Z is always going to be going between 0 down below and up above we'd have 1 minus x squared. So that would be a dz. And we'd have all such vertical bars like this for our dx. That would be x values between -1 and +1. At this point, we'll just allow our TI-89 to be used. I will just cut to the chase. You can confirm this and see that you should get 184 over 35. So some review from chapter 15. This is how we apply the divergence theorem, working out a triple integral of the divergence of your vector field will be a lot quicker to get the flux surface integral value than working it out the way we did the other day. Hope it's going well.